My name is Raoul Schaffranek. I'm head of developer tooling at Runtime Verification. It's a company that focuses on security and a special kind of security. We do formal verification and developer tooling. And this talk is specifically about the last bit, like the developer tooling and one specific tool that we are building. It's free. There's some other tools that we have that you may know us from or not. So we have KVM, which is the longest standing and still maintained formal specification of the EVM. We have Control, which is our formal verification tool that runs on top of Foundry. And then we have Simbolik, which is the topic of today. So this is what I want to do in this talk. So first of all, I will give you a little bit motivation why we need debuggers, or who wants debuggers actually, and then what is the problem with the current generation of debuggers. And then one thing that I noticed is people are using, they are often using debuggers only for a specific task, but there's I think many applications where you can use a debugger. So I want to talk a little bit about some applications for debugging that might be not known to you. But let's start with the motivation. So we are doing this Solidity Developer Survey every year, where the Ethereum Foundation, or now the Argot Collective, they are asking Solidity developers, hey, how do you like Solidity? What are your pain points? What do you like about the language? In which direction should we move on? And since 2020, since the first year we do this survey, we always got response that said debugging is one of the most dreaded aspects of the language so far. And this repeats every year. And 2024 is not on the slide, but let me spoil you, it's the same story. So also 2024, people complain about bad debugging tools. So are we just too dumb to build them? Or why didn't we solve this problem? It's I think it's the most important developer experience problem that we have to solve. But are we just too dumb as an ecosystem to solve it? And let me show you what the current debugger generation looks like, and then you may understand why Solidity developers or auditors don't like them. So this is one of them, and you see there's a lot of low-level details. You get some bytecodes that you can see. There's some, I don't know, some memory, some low-level memory, a stack. And what's very nice about this one is you get actually to highlight the source line where you are stopped. But it's a very low-level tool. You have to be comfortable reading EVM bytecode, which most people are not. Most Solidity developers, they know very well Solidity, but they don't know how to read the bytecode. And that's fair, because bytecode is not meant to be human readable. Bytecode is meant to be machine executable. So there's a gap here. This is another tool. This is from Tenderly. And also you see lots of low-level information spitted out in this output. Now, these tools, I don't want to call them out here. They are doing basically, it's not their fault that they need to show us these low-level details. It's just the Solidity compiler is an optimizing compiler, and optimizations are making debugging very, very difficult. And the Solidity compiler is not giving us, debugger developers, sufficient information to reconstruct the high-level data structures, like the Solidity variables, data structures, data types. So they can only show us these low-level details. But now there is an attempt to fix that. And there's a working group in the Argot Collective that is developing a new format that is called ETH-debug. And the goal of this format is really accelerate the adoption of debugging, make debuggers better. And we recently open sourced a big component of our debugger that is called the ETH-debug Pi library. That is a client-side implementation of the ETH-debug format. And we will see in action how it improves debugging. But because this was funded also by the Ethereum Foundation, we made it all open source so that other debuggers can also use it. And I hope we will see some adoption over the next month or years. So it's already implemented in Simbolik, but the Solidity compiler still needs to catch up. So both sides of the tool, like the debugger and the compiler, they need to work together. We now have it in the debugger, but the compiler still needs to catch up. All right, so this is what Simbolik looks like. This QR code brings you to this website where you can try it out in a browser. So you see it's, I have a laser pointer. It's embedded into Visual Studio Code. That's all I wanted to say you. We're going to see some more examples. So, but let's do it per application. So the original use case for us as a security company was we needed a debugger for our own audits. Because, like, well, you can try to stare down a bug by just looking at the code, but that's a very, like, inefficient way to do it. I think you need to experiment with the code. You need to run the code to see it. You need to be able to pause it, to see, like, to see the contents of the variable at any point in time, to follow the control flow. And the problem really is, well, smart contracts get written once by a developer team, and they are super familiar with the code base. They know, they understand what they are doing, but then if you're doing an audit, then you're new to this code base when you're an external auditor, and you have very limited amount of time to assess the quality, find bugs of the code base. And you don't know where to start. Like, there's maybe, like, the protocols we see today, they are super big, they are super complex. So where do you start? What is the main entry points? How does control flow through your protocol? And the debugger makes this very, very visual. And we will see an example on the next slide. It makes it very easy for you, actually, to just start at any external function, and then you step through the code and see where the control flows. You can see the contents of the variables. You can even go backwards. So, but here's a very concrete example. So, in this example, we were auditing a DEX and a constant product market maker, and we wanted to see how does the swap operation change the balances. Like, that's the most critical part of a DEX is the pricing formula implemented correctly. So the debugger now stopped at this line where Bob is about to perform a swap. We are now before Bob performs the swap. And we can already see what is the balances before two users before the swap. So we see, okay, Alice and Bob, they each have 100 tokens of each token in the pair. And then Alice, in this case, is the only liquidity provider. So she owns 100 shares of that pool. Now, Bob is about to swap 50 tokens A for whatever amount of tokens B we want to know. And even if you know the pricing formula, like doing this calculation, okay, how many tokens will Bob get out there? We sure know it will not be 50 because the constant product market, the formula tells us no, he will get less because, well, Alice should get a fee for, or she get an interest rate for supplying the liquidity. But what is the actual number? You can do that calculation on pen and paper, and actually that's what I did like many, many times, and that's just a super time-consuming process. So, but now I can set a breakpoint, like why did the return statement here in the last line, and I can go there. Now the debugger stopped, and now I can see the new updated balances of each user. So I now see, okay, Alice now has 150 tokens of the first token in the pair. Fair enough, that's the tokens that come from Bob. And Bob's balance has decreased by 50. Okay, fair enough. But how did the other token in the pair change? And now we see, okay, Alice lost 32 tokens, and Bob gained 32 tokens of the second pair. So if you do this on pen and paper, it's really time-consuming process. With a debugger, you just write your test case like this, and then you can immediately see it. Of course, you still have to do some manual math in the background to see that these numbers are actually what you wanted to get out. But at least that you can see it and follow the control flows. So that is, I think that's a big win. So another application for debugger is testing, of course. And well, testing is like an automated technique. We write our tests, and then we can run them on every pull request. The problem is, okay, what happens if a test fails? Like, how why does it fail? Is it a problem with the test setup? Is it a problem in the logic of the implementation? So if there's a mismatch, it could be both. And tracing down the source for the failed test, that's something that's very difficult to do, especially like the more complex the protocol, the more difficult this task gets. But there's an even worse problem, and that is sometimes you can have a test and it passes, and it looks all great, but actually it's passing for a suspicious reason. It's not doing what you wanted to test. So I think a debugger is a great way to run this test interactively, step by step, and see that the assertions that you want to hit are actually reached. Because if it's returning early, or there's a try catch that catches your bug early, it's not doing what you want. So test case debugging is another application. And then forensics. I think that is one thing that the tenderly debugger is really great at. And we always see it, everybody, like after a hack happened on chain, everybody's using the tenderly debugger to follow the transaction, see what led to the exploit. You can also use Simbolik now for the same purpose. You can trace transactions after a hack to do a post-mortem. That's usually very, very difficult to do because the hacks we see today, they are not just calling a transaction, but there's some smart contracts that are deployed by the attackers themselves, and they usually don't upload the source code. So it's very hard to see what the attacker was actually doing. And both Simbolik and tenderly, I think, are great tools to do that. And yeah, I think the story is even a bit bigger because, well, one of the original promises of blockchain was make on-chain activity transparent. But I think this has only partially been achieved. Of course, all the data is on-chain, we can follow it, but then we are looking at bytecodes and we are looking at big hexadecimal numbers and like output that is not human readable. And with a debugger, we can make this output human readable. So I think, like, if you are on the original vision of Ethereum, like bringing transparency on-chain, then a debugger is also a great way to achieve that. Let me show you how this looks like, and I think there's a video that starts auto-playing on the next slide. I'm not sure. So this is a block explorer. I just opened a transaction, and I open it in Simbolik now. And what I can see now, it brings me automatically inside the code, and now I can, like, step by step follow what the transaction actually did. So, and I think this is the benefit that Simbolik has, that it's actually step-through debugging, and you can actually see the contents of all the local variables. So that is something new that no other debugger, I think, can do today. And then this is a very unexpected use case, and we didn't have it on our minds. But then when the Bybit exploit happened, everybody was chatting about blind signing suddenly. And then we realized, well, it's true. Like, whenever we sign a transaction today, we are not really making sure that the transaction is doing what we want. In the best case, our wallet or our ledger will decode the ABI for us, so we can see the name of the function that gets called. But, well, you know, any attacker can deploy any smart contract, call his functions whatever he wants. He won't call his function attack or exploit or steal money, but the attacker will choose a name that makes you believe that the function that you're calling is trustable. So if we only look at the ABI, we are not safe, not at all. So what we really need to do is, before we sign a transaction, we can simulate it in a debugger and see the actual code execute. And if it's a different contract that executes, or the logic is not what you expected, you don't sign the transaction. And this sounds like a really big overhead for signing transactions, because you have to be a very technical person even to follow like what a debugger is doing. But with multisigs and the teams that control wallets that are worth millions or tens of millions of dollars, I think it would be great if you had just one technical person on the multisig that runs it through a debugger and actually makes sure it's doing what they want. I think the Bybit hack could have been prevented, but to be fair, this idea we had only after the Bybit hack. So the tool just didn't exist. Yes, please.
Methodologies do simulation so that they could get around like obfuscated transactions. So they're doing that in real time and simulating what will occur and figuring out how to maximize the profit off of the transaction that hasn't been scheduled yet and jumping in front of the doing flash bringing it right up the line and letting the transaction go through. So they have this basically in real time for MEE bots. So this is something that we should definitely have available to us as well.
Yeah, I think the MEF bots are they're sometimes hidden or working on like hidden transaction pools or hidden mempools that you don't see. And I think this is complementary. So you need these automatic checks, but I think you also need to have a person looking at the transaction that gets executed. Yeah, it's complementary, I'd say. Well, let me go back before this video starts. Oh no, so this is a dep, and now I'm signing a transaction. And again, before I sign it, it actually brings me, like I'm calling the remove liquidity function, and now I can step through the code, actually see, okay, this is the function that I wanted to call, and this is the logic that I wanted to execute, not just by looking at the name. Again, I could call any function remove liquidity, but is it actually removing my liquidity? Is it transferring it to the addresses I wanted to transfer? So that's the assurance that you only get when you really look inside the transaction, not just at the ABI. What does the time say? Okay, I'm going to skip over this DAO proposals thing and this formal verification thing. What I want to show you is how deep you can actually go with debuggers. So this is now for the experts. I don't know, how many of you know how the Solidity compiler allocates a dynamic memory in a dynamic array in memory? You know it, great, but most people don't. And learning this by reverse engineering the compiler is a very difficult task. So with a debugger, we can do that fairly easily. So you see on the code here, we have a dynamic array with 3 items. We can see it stores like 3 strings, hello world and exclamation mark, and then it's just concatenating them and emitting an event. So very simple setup. The purpose is not the contract. It's superficial. It's uninteresting. But we want to now understand how the Solidity compiler allocates dynamic memories and arrays. And we can see, first of all, what is in the array just by looking at the variables. So we can see it here. But if you don't trust the compiler, and there's compiler bugs, we found several, then you want to understand what the compiler is actually doing. So you want to see how does the memory look, how does the array look in the memory. So we can see here now that on offset 60 something, there's stored the array length. You can see it's 3. The next 3 items are pointers to the elements of the array. So the strings are not stored like as a value, but stored as a pointer. And then you can follow the pointer, and you arrive at this offset. And in this offset, you can see there it stores the length of the string, of the first string. So the string hello is 5 characters or 5 bytes long. It's bytes, not characters. And then on the next slot, we can see the ASCII encoding of the string hello. So this blue box here, that's the ASCII encoding of hello. And then we see the ASCII encoding of the string world, and then we see the ASCII encoding of the exclamation mark. And then down here we see that string that is just the concatenated message. I think with some space in between, so the length here is actually 1 character longer. So this is information that used to be really hard to get out of the Solidity compiler. You would run, basically, you would write small examples and you would compile small contracts, and then you would execute a transaction somewhere on your local testnet, and you would open a block explorer to see what happened, or the Foundry debugger, which is really low level, but it does not give you the Solidity variables. So this is something that has really improved now. If you really want to look at the bytecode. Again, you don't have to do that. So you can just look at the Solidity variables. But then if you want to get down that extra level, if you have a suspicion that something on the bytecode level is not matching up, and again, compiler bugs, they are rare, but they happen. And they can be critical. Okay, this would be another example, but I think I save some time for questions instead.
Amazing, Raoul, and I know we're going to have a lot of questions right here. And they're starting already from the front row.
So does the debugger follow execution through contracts?
Follow execution?
Through contracts, yeah. So if a contract calls another contract.
Yeah.
Amazing.
It does that, yeah. So if you have, I think that is pretty standard. Because, well, all the contracts we have today, the protocols that we're seeing today, they are not just a single contract. Like back in the days when we had wrapped ETH, there was just a single ERC20 contract, but all the protocols we see today, they are like complex setups composed of hundreds, sometimes, or dozens of smart contracts, and yeah, it follows the flow of external calls also. And even if there's some external call that is not source code verified, it would let you at least allow it to debug it on the bytecode level.
Okay. And how does it handle storage? Like, do you take a snapshot of the current block, latest?
We are getting basically, what we are doing is basically lazy forking. Yeah. So when the debugger sees a storage operation as load or as store, it will go to the JSON RPC node and request that latest storage slot. And then it will do its own internal tracing because it needs its own, the storage at the block level, the storage, we want to have a finer grained model of the storage. We don't just want to have the storage of the beginning of the block, but also we want to trace it as the transaction keeps updating it.
Thank you so much.
That was actually very hard to implement because even like it's not sufficient to get the storage of the beginning of the block, but there might be a transaction before the transaction that you want to debug that accesses and modifies the same storage slots. So we also need to trace the transaction, all the transactions in the block that happened before. So this makes it really hard to implement, but well, that's not of your concerns because we solved this hard problem. It's not theoretically hard, it's just engineering hard. Like it's time that needs to be invested there.
Thank you. Did you get your question answered or you have one as well? You're good for now. So we have two that came in. I can't see for the lights up here. What makes Simbolik fundamentally different from traditional Solidity debuggers like Remix or X had built-in debuggers?
Yeah, so I think there's multiple things. First of all, Simbolik is integrated into Visual Studio Code. That is, by the Solidity Developer Survey, the editor that is used the most. Then our debugger allows you to really inspect local variables. That's something that no other debugger can do. And then there was this slide that I skipped about formal verification. That means our debugger is not just it's just not a classical debugger, but the name, also Simbolik, comes from symbolic execution, which means you can use it to formally verify your smart contracts. So, well, being a formal verification company, that's one thing that we do. It's basically using math to prove that your test cases cannot fail on all inputs. That's a very simplified way of thinking about it, but I think it's a very intuitive way to think about it. And then, yeah, especially also I think Remix and Hardhat, they don't have this rich ecosystem integration where you can use your debugger for example, to simulate a transaction before you sign it. That's something that is, I think, unique to us. But I'm a big fan of, and I'm a user of these tools. So I think better use one of these debuggers than none of them. Like if Simbolik doesn't fit you, if you don't like it, just try Remix or just try the hard hat debugger. Fair enough. I think each of these tools provide great value. Obviously, I'm biased.
We always are, especially as coders.
Yeah.
Well, thank you so much, Raoul. If anybody have more questions, do catch him outside. He's going to be around most of the day, right? Or do you want to fast go through the last question we have on the board?
If we have the time, I want to go through it.
We can make Mr. Smith wait a little longer, right?
So,
how can Simbolik support smart contract audit? Is it primary for developers or also used for auditors trying to validate assumptions?
no, it's for both. It was born originally, like one-time verification is also, we also do audits. And it was born out of our own need to be better at audits and to save time on audits, because audits are always time boxed. It's really hard to get into a new code base. So our original motivation for developing Simbolik was really just to support our own audits. But then we quickly noticed, okay, developers find this equally useful. But yeah, it's definitely for both groups equally.
That's perfect here. And thank you so much, Raoul. Everybody, please give a hand for Raoul for amazing going through.
Thank you.